welcome you all to day 4 of Cricket Fall Fest 2024, organized by Indian Institute of Information Technology, Tuplaiti Kalyani. We are much delighted today to have Dr. Ritajit Majumdar sir with us as speaker for today's session. First, I would like to introduce our speaker to all of you. Dr. Majumdar is a research scientist at IBM Quantum, IBM India Research Lab, and he's a part of the global quantum enablement and engineering team, where focuses on software research related improving and quality of quantum circuit execution and enablement of both internal and external research to help them achieve utility scale results using IBM quantum devices. He's he did his PhD from ISI, Indian Statistical Institute, and during his PhD, he was a long-term visiting scholar at IBM Thomas J. Watson Research Center, New York, with a Fulbright Nehru Doctoral Research Fellowship. Yeah. Prior to his PhD, he was an assistant professor at BP Podar Institute of Management and Technology, affiliated to MACOT, and remained a visiting faculty there during his PhD tenure also. Uh, Dr. Majumdar is a recipient of the gold medal from Calcutta University for his masters and was awarded the DST Inspire Fellowship as well. Currently, he is also a visiting faculty at the Department of Computer Science and Engineering at University of Calcutta. So, we now welcome Ritajit sir to take charge of the session. The session is yours now, sir. Thank you.
Thank you for the nice introduction. Um, yeah, so very happy to be here in the Kiskit Fall Fest, and I'm really happy actually to see many Kiskit Fall Fest happening in and around Kolkata this time. Um, Around 2 years back in 2022, I was the first one to organize a Kiskit Fall Fest in Kolkata. That was the first Fall Fest in Kolkata. Um, I was still not in IBM at that time. I was still a research scholar at Indian Statistical Institute then, and yeah, very happy that IIT Kharagpur and both Triple IT Kalyani are now actually this year have organized, which are around Kolkata. So and so sorry to all of you for having you to come here. It's a very nice weather, so instead of chilling out, you have to be here to listen to quantum algorithms, and also my apologies there. But yeah, also just before we start, just a thing that we I guess some of you have already been doing some of the lectures by others in this Kiskit Fall Fest. You know that in quantum we have something called this no cloning theorem. So if a quantum state cannot be copied, right? And in our internal meetings, I was just reminded of that. I have joined both from my tablet and from my laptop. My tablet allows me to write things, and I can show some codes or anything from my laptop. So whenever this kind of things happens in our internal meetings at IBM, we just mock the other one and say that this guy has actually violated the no cloning theorem, and they have successfully cloned themselves. So today I have violated the no cloning theorem, and I have successfully cloned myself in my tablet as well as in my laptop. Okay, so let me share my screen, and let me share my screen. Um, we will start with quantum algorithm, and I'll start with the very basic. So let's see how much time permits. The way I want to think of this is, we the way I want to kind of think of today's talk is not to kind of bombard you with a lot and lot of information that this is this, that is that. No, let's try to go a bit slow and make sure that you kind of grasp the ideas that are happening. And obviously the goal is that those of you who are learning from these fall fests, you will be able to go back and teach your juniors, your students, whoever you are, whatever you are doing. So yeah, let's get started with quantum algorithms. So first thing is that when we talk of quantum algorithm, when we talk of classical algorithm, ideally we think of, say, simple algorithms. Let's think of bubble sort, search, and all of those things. When we write down these algorithms, we usually think in terms of pseudocodes, like do this, loop over this, exchange this and this, swap here and there, things like this. But quantum algorithms are not at that level yet. So we need to go down and think in the level of the circuit. Obviously, we can abstract it out mathematically, but in my feeling is that if we just try to keep on writing mathematical formulas, that becomes more cumbersome unless you are like very fluent in mathematics. So let's start with this, and let's start with the first example that came out. So when when quantum came out, there were initial protocols, like I guess you have already learned of teleportation and dense coding and kind of things, that showed that in information processing, in kind of communication, quantum seems to be able to outperform classical. But there was still no example that it is actually useful in computing. We use the term quantum computing very loosely nowadays, but teleportation, dense coding, these are parts of information processing, or you can even say communication. um, when it comes to algorithms, it was first this guy called Deutsch who came up with the first quantum algorithm, and he came up with a nice toy problem. So his problem was the setting of these kind of algorithms is that you can think of a friend you have who has a lot of information, but he's not going to tell you that, oh, I know this, I know that, and I have heard this. If you ask him or her a question, he will answer it back to you. So this kind of very irritating friend is called an oracle in general. So this is called an oracle, and many quantum algorithms are actually in this oracle setting. So an oracle is like that very irritating friend who seems to have a lot of information but doesn't tell us all the information. And thinking mathematically, we will think that the oracle is kind of a function, a mathematical function, and it won't tell me what the function is. I mean, if the oracle would have told me, okay, my function is this, done, game over. But no, you will have to ask the oracle a question, and the oracle will answer back to you. And like this, you have to guess, or you have to not really guess, you have to identify what exactly the oracle is. So that means you have to identify this function if. And the setting that Deutsch came up with is that it's a one bit function, and the function is very simple. So either the function is any of these four, either f of 0 is 0, it's a one bit function, f of 1 is also 0. So, irrespective of whatever you put in as input, the outcome is 0. This is one possibility. Or whatever you put in as input, the outcome is 1. This is another possibility. And what is the other two possibilities? F of 0 is 0, f of 1 is 1. So it's kind of an identity. Or the other way, it's kind of a not. F of 0 is 1, f of 1 is 0. So Doyle said that I am not really interested to know which one of these four this function f is. I am interested more in a global property. So I will call this type of function where the output does not really depend on the input. If you see, the output is 0, whatever you give the input, the output is 0. Whatever you give the input, the output is 1. This type of function, he said, I'll call them as constant functions. And when the output is different, so some at one, for one input it is 0, for other input it is 1, this function he called balanced. And he said that all I am interested in is knowing whether this function is constant or the function is balanced. This is all that I need to know. So forget about Deutsch and everything. If this were classical scenario, what would have you done? Well, the only thing that you can do is you can ask the oracle, you can put in an input and you can get the output. from that oracle. This is the setting, right? So you can give the output input as 0, you will get the output. Is that sufficient to know whether it's constant or balanced? No, because let's say that you put in input 0, you get the output 0 also. So it can be either this or this. We need to know whether it's constant or balanced. So just knowing whether sending 0 gives me 0 doesn't tell me that. Or the other way, let's say I sent in 0, I am getting outcome 1. It can either be this or this. So you will first have to send 0, you will get the outcome f of 0. You then have to send 1 and you will get the outcome f of 1. And now once you know which one of these four the function is, and therefore you can say whether it's constant or balanced. But Doit said that, okay, with quantum I can do better. So how? He said, okay, so look into this. So in quantum, the oracle, so you know that all quantum gates are unitary. So the oracle is also a unitary. So let's call it U of f. It's a unitary corresponding to the function f. We put in, and what does an oracle do in quantum? You put in the input x and you put in a blank state, some state b. It's called b because we just say it's a blank state. And the outcome will be x here and b xor fx here. So from here you can read the output. But Deutsch did something very interesting. So he said that I can tweak this. I can tweak this, and this is how I can tweak this. So instead of sending in x, I will send in a superposition, and you know that we can create a superposition using the Hadamard gate h. So what does h do? Remember, h acting on 0 gives me 1 over root 2 0 plus 1, so it's an equal superposition, and h acting on 1 gives me 1 over root 2 0 minus 1. It's also an equal superposition, the phase is different. So he said that, okay, you give your input, I'll create an equal superposition. In some sense, I'll feed in both the inputs together, and this state I will create in a particular state. It's He created the state in this b state, the blank state that I said. The blank state can be anything. So he created it. He said that I'll create the state here. The qubit will be in this state. Now after this, I will again apply a Hadamard gate here. I don't really care what happens to this qubit, and then I will measure this. And this creates some magic. We will see what magic it creates. So let's try to see what happens at every state. So this is my step 1 here. I apply my oracle, that will be my step 2. Then I apply my Hadamard gate, that will be my step 3. And finally I measure, that will be my step 4. So let's see what happens in step 1. In step 1, we start with x equal to 0, or whatever. Let's say that, let's keep it x. Let's not keep it x equal to 0. Let's keep it x. So what this what these two qubits together will look like x here. So okay, let's before going here, sorry, let's just talk about one small thing, and I'll ask you to just keep this in mind. Let's say that I have this 1 over root 2 x 0 minus 1 over root 2 x 1. This is the two qubit state taken together, this qubit and this qubit. I've just broken it down and written it like that. If I apply my QF, Okay. Okay. So if I now apply my oracle, I mean, if I feed this to my oracle, what will happen? Let's take my 1 over root 2 out. Yeah. Okay. So it is just this, nothing else. And remember what this oracle does, what will happen here. Just remember what we wrote, that my outcome, if B is my blank state, my outcome becomes B XOR FX. This was my outcome, right? So I can write this as 1 over root 2. What happens when you apply UF on this? This will become X remains X. This becomes 0 XOR FX by definition, and my X remains X. This becomes 1 XOR FX. Fine. Now, what can be X? X can be either 0 or 1. So let's see what happens when X is 0. So when X is 0, and we say that fx is also 0, then this becomes 1 over root 2 0. This is 0 XOR 0, that is 0, and this is 1 XOR 0, that is 1. So it is like this. And if x is equal to 0, fx is 1, then this becomes 1 over root 2. So remember from here that I am just talking of this kind of thing. So when input is 0, the output can be either 0, the output can also be 1. It depends on it's a balanced function. If it's a sorry, if it's a constant function, those kind of things. So when fx is 1, this is 0 XOR 1, that is 1, and this is 1 XOR 1, that is 0. So this is essentially minus 1 over root 2, 0, 0 minus 1. You should go back and try to do the same when x is equal to 1 and fx is 0, when x is equal to 1 and fx is also 1, and you will see similar kind of same kind of thing will happen. So I'm not doing this here, but you will see the same kind of thing will happen. So for this kind of thing, I can say that my UF, when my oracle acts on my qubit x, whatever my input x is, but my blank state, this qubit, is 1 over root 2, 0 minus 1. It is essentially minus 1 to the power fx x 1 over root 2, 0 minus 1. Don't get confused if you are. Just look into this. I gave x as my input, that remained same. I gave my blank state as 0 minus 1 by root 2, that remained same. Here also, here also. What changed? Here I have some sort of a plus 1, I can say. Here I have a minus 1. And I can think of it as what really changed. So you can think of this as minus 1 to the power fx, that is 0, so that gives me 1, that is why the 1 is here, and this is minus 1 to the power fx, which is 1, so that gave me minus 1. So in a general way, I can write it like this. This is called phase kickback, and I would kind of request you to actually um, remember this will come handy whenever you are learning quantum algorithm, be it today, be it later on when you go and learn more interesting quantum algorithms yourself. This will always come handy, this idea of phase kickback, that if you create your blank qubit in this particular state, then irrespective of whatever the input is and whatever the oracle is, the output becomes like this. The information of this oracle, this function, comes to the phase. So that's why it's called phase kickback, that whatever was the information was in this bit domain. So it was in this oracle. That information gets transferred to the phase. So that's why it's called phase kickback. So now let's take our original problem. We have this x on Hadamard. So let's say my x is 0. Let's say my x is 0. So when I apply Hadamard on this, I know this becomes 1 over root 2, 0 plus 1. And I already have my second qubit as 1 over root 2, 0 minus 1. So this is my state here. In step 1, this is my state. The first qubit is in 1 over root 2, 0 plus 1 when the input is 0, and it is in 1 over root 2, 0 minus 1. Uh, that is how we have created the blank state. Now, let's come to, we can even break it down if you want, but yeah, let's break it down like this. Let's break it down by saying that um, this is 1 over root 2, 0, 0 minus 1 by root 2. So we are just distributing, um, plus 1 over root 2, 1, 0 minus 1 by root 2. So we have just distributed the first qubit. Now let's come to step 2. What was step 2? We apply the oracle. So the oracle, whatever it is, that gets applied. That is step 2. So what happens when we apply the oracle on this? That's how where the space kickback immediately comes into play. When the oracle acts on this, the phase is the bit information, the information of the function gets to the phase. So for this first portion, it will be 1 over root 2 minus 1 to the power f of 0, because the input is 0, the x is 0 here. So minus 1 to the power f of 0, remaining whatever it was, it remains the same, plus 1 over root 2 minus 1 to the power f of 1, because this is 1, the remaining portion is whatever it is, right? So I can write this down as 1 over root 2 minus 1 to the power f of 0, 0 plus minus 1 to the power f of 1, 1. And the second qubit is, you can think of this second qubit as a catalyst, and we will be very like bad friend, and we have used the second qubit to do this phase kickback. Now that it is done, I don't really care what happens to it anymore. So that's what we kind of wrote here, that we just drop the second qubit after this. So once this portion is done, the phase kickback is done, I don't care uh, what the second qubit is happening to the second qubit, we just throw it away. So let's look into this. We can write this, let me write and then we can explain. We can write it like this. Why can we write it like this? So it's like I am taking f of 0 as common, right? So let's say, uh, let's think that if 0 is 0, if 1 is also 0. So this is just 0 XOR 0, because nothing happens. What happens if 0 is 0, if 1 is 1? Nothing happens. You are taking 0 out. So it's 1 XOR 0, nothing changes. On the other hand, let's say that f of 0 is 1. Now, if f of 1 is 0 and you are taking f of 0 out, this will become 1 XOR 0, and so that will become 1. And similarly, if this is 1, so on. So it's kind of like we take common here, so we have to put in the term here because we have taken a term out. Now, now is the interesting thing. So let's look into this algorithm once more. What happens if my function is constant? Let me write it here. I don't know. Let me write it here. What happens if my function is constant? What is f of 0 XOR f of 1? Well, if my function is constant, either both of them are 0 or both of them are 1. So if I do an XOR of both of them, it will always be 0 if it is constant function. On the other hand, if it is a balanced function, then one of them is 0, the other one is 1. I don't care which one is which, but 0 XOR 1 or 1 XOR 0 is 1, right? So think of this. If it is a constant function, at this moment, your state is 0 plus minus 1 to the power, what was our thing? 0. When the function is constant, minus 1 to the power 0, 1, which is 1 over root 2, 0 plus 1. And if my function is balanced, then we have minus 1 f of 0, 1 over root 2, 0 plus minus 1. When my function was balanced, this XOR was 1, so it is minus 1 to the power 1 times 1. So that is 1 over root 2, 0 minus 1. Now, those of you who are actually following properly, you are going to be very angry that what happened to this? You were writing this portion and in the next part you just forgot about this? No. See, this is what, so when we measure this state, when eventually we will measure, right? So when we measure this state, this is what becomes a global phase. And in quantum systems, global phase remains undetected. So two states, I'm sure you know that. If not, just just remember this, that if you have a state psi and if you have some state with a global phase psi, and if you measure both the state, from the outcome you cannot differentiate between this and this. So it doesn't really matter if I drop this global phase. So that's why we have dropped this global phase. Now we have this kind of thing. What was our step 3? Our step 3 was we apply a Hadamard. Well, let's apply a Hadamard, and we know what will happen when we apply a Hadamard. What does Hadamard gate do? Hadamard takes 0 to 1 over root 2, 0 plus 1, and it's obviously a reversible gate. So it's when you apply Hadamard again, this comes to this, and when you apply a Hadamard again, this comes back. So when I apply a Hadamard on this, this becomes 0, and when I apply a Hadamard on this becomes 1. So now if I measure and I get my outcome as 0, what is my deduction? My function is constant. If I now measure and I get my outcome as 1, my deduction is that the function is balanced. Obviously, I don't know which one of these two, and I don't need to know. So that's how we started the premise that all I need to know is whether the function is constant or balanced. It's a global property that we were interested in. And we kind of previously saw that when we were doing classically, we need to do, these are called queries to the oracle. We need to do two queries to the oracle, one with 0, one with 1. But when it comes to quantum, a single query is sufficient. So we have been able to do only one query, and we know whether the function is constant or balanced. Great. So two things can happen now. Those of you who are actually following, and those of you who are very optimistic about quantum, you can say, oh wow, like quantum really works, because we already have seen an example where quantum is better than classical. We needed two queries in classical, now we need only one query in quantum. And those of you who are maybe not that optimistic, or you can say, yeah, whatever, like you are going from 2 to 1. I mean, who cares? You are going from 2 to 1. And you just designed a problem. but who cares about this problem even? Like this problem has no physical implementation or any physical needs, right? So you have kind of very cleverly generated a problem, which is kind of a toy problem, has no actual real life implementation, and there you are showing that quantum is great because it can go from two queries to one query, blah, whatever. So this is a very valid reaction if you are having this reaction at this moment, but stick with it for some time, and keep two things in mind. Just to repeat, because we will need this. Keep two things in mind. One thing that we learned is phase kickback. So what was our phase kickback? If we apply UF on X and the second qubit is in this particular state, then the information of the function raises to the phase. So that's why it's called phase kickback. So this is something that we want to know. Just one point: when I did this calculation, I did this with x equal to 0. Please try it out yourself with x equal to 1. You will find the same result. There is another thing that we really need to think is how an Hadamard gate works. So we already know how it works, but just to generalize it in some sense, we know that Hadamard gate acting on 0 is 0 plus 1 over root 2, and Hadamard gate acting on 1 is 0 minus 1 over root 2. So we can say Hadamard gate acting on some qubit x is sum over z minus 1 x times z. So what just happened? If you are lost what just happened, let's try to go from this to this, try to go from this formula to what we already know. So h acting on 0 is, so 0 can be either z can be either 0 or 1, so it's sum over, so it's minus 1 0 into 0 0 plus obviously there is this 1 over square root 2 to the power n, um, plus minus 1 to the power 0 into 1 1, and with the normalization, so this is our known 0 plus 1, and h acting on 1 will be minus 1 to the power, well, my x is now 1, z is 0 0 plus minus 1 1 times 1, oops, times 1 1, so it is 0 minus 1. So it is just a more complicated way of writing what we already know, and this holds for any qubits. This holds for any number of qubits, not just for one qubit. So keep these two things in mind, that what we learned about phase kickback and what we learned about how we can write the action of a Hadamard gate. And let's address this question. I hope you had this, that okay, yeah, you just came up with a problem that has no physical implementation, real life practicality, and you went for two, from 2 to 1, and you are suddenly saying quantum is so great. um, and even the name of this talk is overpowering classical. That's not great. So let's take a different scenario. Here, my function is something like this. So it's an oracle where you can think of this in terms of cryptography or something. It's an oracle where you pass in a bit x. Say it's a 4-bit system. Say it's 1011, and there is already a fixed a. You should be, those of you who have studied a bit of crypto, you should find some um, similarity with the one time pad. So let's say one is one, say a is 1101, This is not known. This is something that only the oracle knows. So think of a scenario where my oracle is sitting here. It has some a which nobody knows, and the user who is sending the message passes in x, and the oracle creates this x into a, that is bitwise multiplication. And so this will become something like, if we do this example, x into a will be 1 into 1 is 1, then 0 into 1 is 0, plus no, sorry. It's 1 into 1 is 1. Next is 1 into 0 is 0. Next is 1 into 0 is 0. And last is 1 into 1 is 1. So it is kind of encoding and passing in something that is x times a, bitwise multiplication. So you can think of this as an encoding scheme, right? And this, obviously, you can understand, has some practical implementation. But we will be like a hacker, and we will try to understand what a is. I want to hack the system. What is a? This is what I want to know. If I know a, I can hack the system. So in classical, what can you do to know a? Let me answer here, and you can go back and try to see if you can find something better. If you can, write a paper on that. So let's say it's a 4-bit system. Whatever a is, let's say a is a0, a1, a2, a3. It's 4-bit for this example. First, I will pass in 1 0 0 0, and what I will get back is a 0 0 0 0, because the remaining things will get multiplied, and that will kind of create 0, right? So I can so from this, if I look into this, I get to know what is a0. Next, I'm sure you can understand now. Next, if we pass in 0 1 0 0, we will get 0 a1 0 0. We know a1, and so on. So if it is an n-bit string, you need to pass in n values, and then you will get each of these a0, a1 up to an for each of these inputs. And once you have all the values, you know a. So you need to send n queries to this oracle, which you can think of like an encoder. Now, in quantum, what we can do? So again, we will come to the quantum circuit. It's an n-qubit system, and we apply Hadamard on all n of this. It's exactly the same circuit as we were seeing for the Deutsch algorithm. My second qubit is in the same 0 minus 1 over root 2. So what is the this state? We know this is the equal superposition of all qubits, right? Because Hadamard acting on 0 gives 0 plus 1 over root 2. If it were 2 qubits, it will be 0 0 plus 0 1 plus 1 0 plus 1 1. So all of those will come. It's an equal superposition. So for n bits, I can write it like 1 over square root 2 to the power n sum over x, where x is like all the 2 to the power n terms. This now goes in my oracle. So it's I am a quantum hacker now, and I am still trying to understand what is a. That is still my goal, and I am passing in this equal superposition state with this uh, extra qubit in this particular state to the oracle. Now, what will happen? Remember one thing I requested you, that please remember this. Remember phase kickback. Whatever the input is, if this is my blank state, then the information of the oracle comes to the phase. So this will become 1 over 2 to the power square root of 2 to the power n. This is the normalization. This will become minus 1 to the power fx x, and this qubit remains as it is. And again, I'll be a very bad friend to this qubit, and my work is done. I don't really care what happens to you anymore. So, what is f of x? Well, it is x into a. So let's replace this with x into a, right? Now we just go and apply a Hadamard once more, like Hadamard on all qubits once more. Let's come to the second thing that we wanted to remember, that a Hadamard gate acting on X looks like this. So if you see here, it's like instead of Z, you have A kind of thing, right? It's the same structure, and Hadamard is its own inverse. So if you apply this, you will get back A. It's obviously an n bit string. It will be an n qubit. So A is essentially like A0, A1, an minus 1 in bit. So what happened here? This is called the Bernstein-Vazirani algorithm. Bernstein-Vazirani algorithm. So what happened here? We have a problem which looks very which looks more practical at least than what the Deutsch algorithm was. There was no practicality to that scenario. We have a scenario where it's almost like encoding in communication. We are kind of doing some encryption of our communication bit, and we are sending it over the channel, and there is a hacker who wants to hack. The hacker can hack the system classically by doing n queries. Now n can be large. Say you are sending 1,000 bits or whatever. You have a huge system, 1,000 bits, 2,000 bits, 10,000 bits. So whatever n is, you will need to put in that many queries in classical. Whatever n is, you need a single query in quantum. So this is powerful, and you actually have a practical example of quantum actually overpowering classical. Let me maybe pause, and if there are any questions, we can take that at this moment. If not, if not, let me now come back and ask the similar question. So I mean, I'm sure you have heard of this Shor algorithm that can break RSA crypto systems. This was a very simple scenario. Shor algorithm can actually break RSA crypto system in polynomial time. So the question naturally comes up: how come our security systems are still using classical encryptions and they are still secure? So let's see an example here, and let me so let me just come back to this. I hope this is visible. Yeah, can any of you confirm if this is visible?
Yes, it is visible, sir.
Okay, good. So this is a Qiskit code of the Bernstein-Vazirani algorithm itself, the one we just learned, and we are just creating this oracle here. Let's not worry how to create the oracle. Let's say that our secret string, okay, I called it A, right? So let's say that our secret string is A, and it is 1011. So let's look into the circuit, how it looks like. Remember what we did? So all qubits in quantum hardware, they start with 0. So we have a 4 qubit system. So we have 4 qubits here, and we have a single qubit which should be prepared, which is the ancilla qubit, which should be prepared in 0 minus 1 over root 2. And how do you prepare it in 0 minus 1 over root 2? You apply Hadamard gate on 1. So on the last qubit, which is the ancilla qubit, the blank qubit we were talking of, we have changed the initial state to 1 and then applied Hadamard, and that is creating this state 0 minus 1 over root 2. So what was our original protocol? The original protocol was that we will apply Hadamard on all qubits, then we will apply the Bernstein-Vasiliani oracle, we will again apply Hadamard on all qubits, and then we measure. Remember, when we measure, this qubit is the ancilla qubit, which we don't really measure. So if you see, I haven't measured that qubit here. I have just measured the 4 qubits which I am interested in. So let's go ahead and run it on a simulator, and ideally we should just this one circuit should be able to give me back this a equal to 1011, right? And we see that it has been able to give me. So remember that we in Qiskit we read it in the opposite way, so it's 1011. So we have been able to retrieve 1011. We have already seen it mathematically, so we knew it will work, so that's not a big deal. uh, but what we know is that current quantum systems, they are noisy. So if you go to this IBM Quantum Experience platform, if you are already not here, please be here. Create a free account. It's a free account that you can create. Um, and each of you will have an API token. All of you will get like 10 minutes free usage monthly. And for those of you who are thinking what will happen with 10 minutes, see that I have already run a single job here, and that was actually for the other Fall Fest, and it took 2 seconds. So you understand 10 minutes is a lot when one's job, when you are running a single job, that takes 2 seconds. 10 minutes is a lot. So here, if you see what are the quantum processors that we have here, you will see that these are like the quantum processors that you will have access to, 127 qubit devices. And let's look into one of those, let's say Sherbrooke. Um, you will see that there are many error informations of this. So each of the gates have their own error. So when you are applying 2 qubit gates, they will have their own error. When you are applying single qubit gates, they will have their own error. Measurement is erroneous and everything. But think of one thing, that a single qubit gate, if you see, this is in the order of 10 to the power minus 4. A 2 qubit gate error can be in the order of 10 to the power minus 2. So it's almost 100 times more noisy. So current systems are noisy, and if you run this, I have taken a fake backend because otherwise you will see that we have actually queues. So yeah, there are actually 138 jobs pending. I don't want to send a job here and like wait awkwardly for hours here. So Qiskit allows you to use these fake backends which actually mimics the real backends. And this is a 27 qubit device named after Kolkata. So let's create this fake backend. And if I run it on my noisy backend, you see that there is some probability that I will get other results as well. And this is coming because of noise, because we have seen mathematically and we have seen here um, numerically as well that this works. And if we go to bigger size of problems, let's say we have a much bigger size, it will be a much bigger system, and we will still get the outcome properly in real life scenario. But if we run it on a noisy scenario, you see that previously we had almost a probability of 98% of getting the correct outcome. How big did I give? Um, okay, wait. I gave a bit too big. Sorry, I gave a bit too big. It will take too much time to run. Let's make it a bit smaller. 10 qubits should run. So if we run it, see now you previously when it was 4 qubits, you could see that we had almost 98% chance that we will get the correct outcome. So you could say that okay, I mean, great, why not? 98% is good. But now with 10 qubits, you are down to 84% of correct outcome. And ideally, when we think of communication, the bit size will be in thousands or even more that we even can't simulate here. So you can understand that these kind of algorithms that we are learning, that we know that they overpower the um, classical algorithms, they are a bit difficult to run in current scenarios where the systems are noisy. Well, the system noise will remain always, but we will get error correction in say 2029 to 33. That's in the IBM roadmap, and then perhaps we can start running this kind of things. So I'll just take maybe 5 minutes if that's okay. So what we can do today is that we can run other kind of circuits which are called this hybrid quantum classical circuits. Forget this. These are called the hybrid quantum classical circuits. So let me just show you how this works. So the way of hybrid quantum classical circuits is that, okay, you are saying that running a big quantum circuit is difficult because there is noise. Why not partition your entire workload into some classical portion and into some quantum portion, so that your quantum circuit is still small and you can still execute it faithfully even when there is noise in the system. So one example we are taking is a graph problem. Let's say this is a very simple graph and we want to find what is called the max cut of the graph. So what is max cut? The idea is that you want to color your vertices in such a way that, so whenever you have an edge and the colors of the two vertices of that edge are different, we say it's a cut. So you want to actually color your vertices using two colors only in such a way that the number of such edges where one of them is blue, the other is yellow, is maximized. This is one possible coloring for the example that we have here. Um, so these kind of algorithms work like this. So when you don't know the answer to a problem, what do? We guess, right? So this is what it does. It creates some quantum circuit that comes from the graph theory, which we will not go into. So this QPU, this parameterized circuit, comes from the exact graph theory, and from the graph we can have scenarios how to create these Hamiltonians. But we create this parameterized circuit. How do we know what are the values of these parameters gamma and beta? Guess it, because we don't know. So you run this circuit, you get the outcome, you calculate an value from that. It's called the expectation value. And in terms of this problem, this expectation value will give a value of the cut. We want the we want to maximize the number of such edges, and this expectation value will give you a number of that edge. So maybe your guess of these parameters was very bad, possible. So what you do is you pass it on to a classical processing unit. It will update the parameters, and then you go and try again. And if you see that okay, my now next result is better, you go and do again. So you try to get the best parameters in a loop like this. So this is what is called a hybrid quantum classical algorithm. Although I showed here in terms of graph problems, this type of hybrid quantum classical algorithms are used right now in many different fields. So for example, quantum chemistry is a huge domain of application. Quantum machine learning has this exact same scenario, because there instead of calculating number of edges, you calculate some f1 score of or something. So there are many such applications. High energy physics, if anyone is interested. So what we do, we simply create this quantum circuit. I won't go into the details of how this quantum circuit is coming, because it will require some mathematical details of the graph theory. And we start with some initial parameters because we will guess, right? We don't know what is a good value of parameter. So let's say that we guess it's all zero. And if you see here, we call this scipy.optimize. It's a classical thing. There is nothing quantum. So what it is doing, it is passing this parameter. It is running the same circuit with this value of parameter. It is calculating the expectation value, which gives the number of edges that has been cut, and it is returning it to this minimize function, which is actually using this method. Here I have used this Kobila optimization method. It's using this Kobila method to find the next set of parameter, and it is again calling this obtain exp val with the new set of parameter. So as you see that this will go on happening, and if you see this happened 56 times, this nfave is the number of times this looping went on, and we have this 56 times, and we have these values of parameters. These are the good values of parameters that we have from this optimization. And how do we know that? See, when we use these good values of parameter, so see, I have used this nice good values of parameter to assign this to the quantum circuit, and I am running this, I get the outcome 0101 or 1011, both with equal probability. Now you can interpret, let's say that 0 is blue, 1 is yellow. So 0101, see, we already have seen here that blue yellow is a good solution. So uh, 0101 is a good solution, and we have that with probability 50%. And if you haven't already understood why 1010 is also there, why does it matter if I would have used yellow here and blue here? I could have just interchanged the color, right? Blue yellow is same as saying yellow blue. So both 0101 is a good value and 1010 is a good value, and we see that we get both with equal probability. And rather, we what I mean is that if you add these two, you get probability almost 1. So with very high probability, you get the actual outcome that we need. So this is how the near term quantum algorithms are designed. We kind of delegate some of the works to classical processing unit because quantum systems are still noisy and we still cannot do error correction. So we delegate some part to the classical system and some part to the quantum system. They act together, hands on hand, and then they can solve real life interesting problems. We already see that this is a graph theoretic problem. You can similarly run a machine learning problem here. In qubits, you feed in data. You can run a quantum chemistry problem here. You then create the circuit in terms of orbitals and everything. You can run high energy physics problems here and many things. So yeah, I guess we can stop here. So this is what I wanted to talk about. Now if you have any comments, questions, we can take that.
If anyone is having any query, you can unmute and ask.
Okay, if not, um, no, no. Okay, that's a very interesting question. You, when you say that you can solve NP-complete problems, I think you mean in polynomial time. There is no such proof that with quantum computers you can solve NP-complete problems in polynomial time. So what I mean is that there is no proof that P is equal to NP in quantum domain. So Shor algorithm doesn't belong to NP complete. It's an NP problem. There is one proof that a particular NP problem, which is this integer factorization, can be solved in polynomial time in quantum systems. For example, in Grover's algorithm, we didn't cover that. It was not possible to cover in this time. In Grover's algorithm, you will see that we can get a quadratic speed up over classical. So it is still exponential time algorithm, but what would have taken you to the power n order will now in quantum take you square root of 2 to the power n or 2 to the power n by 2. This much speed up you can always get using a quantum system, but there is still no proof that you can get such a speed up that 2 to the power n will become um, n or something for NP complete problems.
Okay, participants, if you have any question, you can ask here, or you can fill up the, please everyone fill up the feedback form. It is also shared in your Discord. You can ask any question in the Discord later also, if you think, and then we'll forward the question to the speaker. But better you can ask it now.
What is about discrete log problem like short circuit and short circuit?
Sorry, it wasn't very clear.
Yeah, what is about discrete log problem?
Yeah.
From Simon's paper to shorts, how Simon's paper will be corrected by shorts. Like what are the things? What is the catch?
Yeah, I mean, shorts papers show that you can do discrete log problem also in polynomial time, but even the discrete log problem is not NP complete. So it's like if you see shorts algorithm, what the only thing it shows is that you can reduce these problems, this factorization or discrete logarithm kind of problems, to period finding, and period finding is really fast using a quantum computer. So it's the period finding portion that you can speed up using a quantum computer. Everything else is classical, before and after. And yeah, the period, I mean, there are many steps to that. The period finding is faster because Fourier transform in quantum is faster. So these all steps will come one after another, and you can obviously get a big speed up in quantum, but it's still not like an NP complete problem that is getting solved. If like
Yeah,
that was your.
yeah, yeah. But see, the thing is that what we found in what Shaw has written in his research paper, what Simon says right in his wrote in his research paper. But the thing is that we are just student, right? So we just can't go the step by step process. What are the mathematics? What are the kind of thing that each and everyone can go for step by step and understand this period finding or discrete log problem can solve quantum computer uh, very easily. Is there any kind of material for that step by step?
I would say that go to the Kiskit Global Summer School of 2020. There,
20.
the 2020, that is the first Kiskit Global Summer School. You will find the videos in YouTube, and there they have actually shown all these period finding problems and everything, and it's done in really nice way. So maybe you can follow those that video. Just one thing is that don't go to learn the codings in Qiskit that were taught in 2020. They are all outdated. Like if you learn coding from that 2020, nothing will work now. but you can go and learn the mathematics. It was really nice.
Okay. Thank you. Thank you. Thank you.
Yeah, I hope here we can conclude. Samantha, sir.
Yes, sir. Yes, Tejas. Okay. I think there's no question in the chat also. Yeah, one question I have
There is
received.
a question.
I mean,
Should
see, I
I
mean,
repeat or for you?
you can. No, I can see like if you want to go for quantum algo, the first thing I would say, I really don't know your mathematical background, but if you are trying to go for algorithms beyond variational algorithm, you need to know the encoding portion, like how to create that quantum circuit that has an underlying mathematics. But for other cases, just make sure you understand the mathematics very well. So for other types of algorithms like Grover, quantum, Walk, and everything, there is a lot of probability and linear algebra that goes into this. So if you are interested in those kind of quantum algorithms, then please just go ahead and learn those mathematics. Um, one really nice, so for each and every one of you, I would say that go to the IBM Quantum Learning Platform. The IBM Quantum Learning Platform, it's not because I am coming from IBM that I am saying this. Uh, IBM Quantum Learning Platform is by far the best learning platform that you can have in quantum computing. There is a course by John Watrous. He was from University of Waterloo. He's in IBM now for a few years. Um, it's completely mathematical. If you really want to learn all these query algorithms and more, even the information processing, go ahead and learn those things from that course by John Watrous. And for the coding portion, you can even see the other Qiskit oriented courses even there in the IBM learning platform. Quantum ML, there has been a Qiskit Global Summer School, I think 2021 itself was Quantum ML. So, yeah, you can see those videos. Like the Global Summer Schools are really great. You should be following those videos. There is still not a course in learning platform on Quantum ML, but it will come. It will come soon.
No, sir, one thing.
Yeah.
Actually, I have tried quantum classifiers, and in the IDS dataset, I have trained a model in quantum classifiers, the VQC. It gives
Hmm.
an accuracy of 76%. That's the maximum I got, but it's way lower than the classical ones.
I mean, see, it's difficult. First is that I am not an expert in machine learning, so and it's very difficult to say like this that why you obtained a accuracy of 76%. There are many things in quantum ML that you can try out. I mean, you can try out different answers. You can try out different encoding schemes and everything. So maybe changing those, maybe having more data will help, but at the same time, please keep in mind one thing, that whenever you are dealing with these kind of near term algorithms, I guess the 76% is with noise or with simulation. Because if it is with
With
simulation,
simulation.
yeah, see, the point is that if it is with simulation, then this kind of result, I mean, yeah, not discouraging you, but this kind of result hardly has much importance. The reason for that is that the fact that you were able to simulate it on your laptop or whatever computer means that this is doable classically. It is only when you can actually go to real hardware, or at least, I mean, at least show that even in the presence of noise, this kind of things are like you are getting this kind of accuracy. Your accuracy will reduce when the noise comes, is when this result makes any sense in terms of research. So yeah, there is no proof as of yet that quantum machine learning can outperform classical machine learning. So yeah, just keep that in mind when you are dealing with it.
Could you just help me with some, I mean, how should I run this in a quantum computer?
I mean, yeah, I mean,
That classifier model?
it's just some quantum circuits, right? The way you run
Hmm.
quantum circuits, the way you are running it on, say, some AER simulator or something, you can instead just run it on a real quantum computer.
It's available in IBM, right?
Yeah, yeah.
Okay.
Sir, yeah.
Yes, yes.
Sir, to do internship or land a job in or work with IBM Quantum, can you please guide us?
So we already have an internship opening right now for next year summer 2025. It's open up to 31st October. If you are interested, go ahead and apply. Um, So the eligibility in terms of logistics is that you should still be a student in 2025 and you should not graduate. I mean, a student can be undergrad, grad, like bachelor's, master's, PhD. Everyone is a student, but you should not be completing your course in 2025. That is an eligibility, logistic eligibility. In terms of other kinds of eligibility, we usually want that you should have like a proper understanding of the basics of mathematics of quantum computing, and not just saying that, um, not just what is a qubit, what is superposition, also like how do you calculate expectation values and things like this, and also like Qiskit 1.0 or higher. Very strong background there.
Sir, I applied for that internship.
Okay, great. All the best.
Okay.
Well, any question? I think if not, Tejas, you can end with this ending note. And I would like to thank Ritojit. It's a very nice and informative talk, and I hope that it was helpful for the participants. Thank you, Ritu.
Thank you for the.
Yeah. Thank you, sir. Thanks a lot from Juplaiti Kalyani and QScript team.
Thank you.